So this screencast is going to focus on calculating entropy changes for a chemical reaction, and this is very similar to what we did with delta H values when we did products minus reactants. So we're going to go through this fairly quickly. The first gives you an example of the formation of ammonia reaction, and so it says we've basically got 4 moles of gas forming 2 moles of gas, and so they ask you the question, does this increase or decrease entropy? And so on the product side, there is less disorder. So there would be a decrease in entropy. And so then they follow up and say, well, would that delta S sign be positive or negative? So anytime there's a decrease in disorder or a decrease in entropy, that means we have a negative delta S. And so they go on to talk about, the amount of moles of gas, which is kind of a review from what we did before. So, for example 2, you'll notice that we've got lots of different phases here. We've got aqueous, solid state, forming aqueous, liquid, and a gas state. And so this talks about the fact that you have lots of different states, and it's difficult to kind of tell what's happening with the reaction. So for reactions where it's not so cut and dry as to whether there'll be an increase or a decrease in disorder, it's important that we have a way to calculate that entropy change and to know how the entropy of the system will change. And so this should look very similar to you because it's the exact same thing we did when we calculated enthalpy with the delta H values. So these values are listed in tables in the back of your book, or they may be embedded within the problem. But all we're going to do is products minus reactants, but we need to remember that N is the number of moles, and we'll take the coefficients when we go to multiply through. So the first practice they give us asks us to predict, and so here we've got 2 moles of a solid and 3 moles of a gas, forming 2 moles of a gas and 2 moles of a solid. So if you kind of think about it this way, these two kind of, cancel each other out because you have 2 moles of solid. So really what we have is 3 moles of gas going to 2 moles of gas. And so we would predict that the product side has less disorder. So we would predict that our delta S for this reaction would be negative because disorder is decreasing. So they give you these values. Again, these values come from tables. You'll notice that things that are in their in their elemental state, like O2, if we looked up the delta H value for O2, it would be 0. By definition, the enthalpy values are 0, but you'll notice that they are not 0 for delta S, because this has to do with disorder. It's also important to note we've got these 2 gases here, and their delta S values, their disorder values, are much higher than these guys that are solid state, right? So when we go to do our delta S for the reaction, we start with our product side. So don't forget it's products minus reactants. So we'll do 2 times SO2's value, which is 248, plus 2 times nickel oxide's value, which is 38, and then minus 2 times nickel sulfide, which is 53, plus 3 times oxygen's value, which is 205. So don't forget that it's minus this whole sum. And so delta S reaction for that comes out to be negative 149 joules per Kelvin. Now notice these were given as joules per mole Kelvin. Mole does not appear here because these guys are moles, so we're multiplying through by moles. So as predicted, our delta S value is negative. Alright, in the next section they show you different ways that you can calculate Gibbs free energy. So just to recap, we said that Gibbs free energy is the final say on whether a reaction will be spontaneous. We need it to be negative if we want it to be spontaneous, and if we get a positive, that would be non-spontaneous. So we look at these values. We've got the same formation of NH3, right? They tell you that delta G is negative 33. So that would mean that this is, sorry, not exothermic, this would be spontaneous as written. So there's 3 different ways we're going to look at calculating delta G. And so the first way is very straightforward. We just go to the tables in the back of our book, or we can look the values up and calculate delta G doing products minus reactants. So if you have those values, now the problem is you may not always have those values, but if you have them, you can certainly just do products minus reactants. So we're actually going to keep with the same reaction for the next 3 problems, and so we're just verifying that there's 3 different ways that you can find delta G. Alright, so here we've got products minus reactants. So for delta G reaction, we'll start on this side. So 2 times CO2's value plus 2 times water's value minus 1 times C2H4's value, and then oxygen you'll notice is 0. So we get a delta G reaction equal to negative 1314 kilojoules. So when we look at these other 2 ways to find delta G, we should get a similar number to that. So that's the first way. Just if you have the delta G values, do products minus reactants. Alright, the second way to find it, and again, I want you to imagine that these aren't there. So let's think this is a scenario where, oh, we go to the tables and we can't find those delta G values. But we do have delta H values and delta S values. So if you think back to our Gibbs free energy equation, to find Gibbs free energy, it's the enthalpy minus T delta S, right? So we don't have a straightforward delta H and we don't have a straightforward delta S, but we have these values. So we could find delta H reaction by doing products minus reactants. And we could find delta S reaction by doing the same thing. So we're going to do that. Alright, so we want to make sure we do products first, so we're working on this side first. So for delta H, 2 times CO2's value, negative 393.5, plus 2 times water value, negative 242, then minus reactant side, 1 times 52, and then the oxygen is 0. So delta H reaction comes out to be negative 1323 kilojoules. Alright, so then we go to do delta S, do it right here. Now we're looking at this column, 2 times CO2's value plus 2 times water's value minus C2H4's value plus 3 times oxygen's value. So delta S comes out to be negative 28, and be careful because this is joules per Kelvin. Okay, so now I've found my delta H and my delta S, and so now I just do negative 1323 minus temperature, which I believe was 25, yep, so 298 Kelvin, and then times, we want to be careful because this is in joules, so I need to change it to kilojoules in order for the math to work. So I come up with negative 1314 kilojoules for this reaction. Alright, and then the last way we're going to see that we can calculate delta G is by using multiple reactions and actually applying Hess's law. Remember that Hess's law said that the order really doesn't matter as long as you sum up to the final reaction. Each of those energy steps will also sum up to the final reaction. So remember some of our strategies for knowing what to flip and what to multiply through by. When you see things that don't appear in the final reaction, like when I see C2H6, I know that has to cancel, so we do want them to be on opposite sides. Looking for making sure your reactants are on the correct side, so C2H4 is on the correct side there. Hydrogen does not appear in the final reaction, but I do see it here. I know I can't flip this one because C2H4 is on the correct side, so that means I'm probably going to want to reverse this one, and when I do that, the sign of delta G will become positive. The other issue is I don't want to double this, but I have 2 hydrogens here and only 1 there. So I'm going to try multiplying this by 1/2 and see if that helps us. So now we end up with H2O forms H2 plus O, let's see, 1/2 O2. And so our delta G will be positive 458 over 2. Okay, so then let's get rid of that so we're not tempted to use it. So let's see if there's anything else we have to do. I'll switch to a different color here. Alright, so when I do that, hydrogen's gone. That's one problem solved. I've got 3 waters on this side and 1 water here, so that 1 water is going to take away and make 2 waters, and that's good. 2 CO2s is good. I have 7 halves O2, which is like 3.5. Here I have 0.5, so if I bring that to the other side, this oxygen's gone, and this is just down to 3. And then C2H6 and C2H6. So to get my delta G, I'm just going to sum up negative 1442 plus negative 101 plus 458 over 2. And I get a delta G of negative 1314 kilojoules. So here you saw 3 different methods for calculating delta G, and you notice that we end up with the same answer for all 3 of the scenarios.